Section 17.5, the Tukey multiple comparison procedure. The Tukey multiple comparison procedure that we will consider here applies when the family of interest is the set of all pairwise comparisons of factor level means. In other words, the family consists of estimates of all pairs, D equals mu I minus mu I apostrophe, or of all tests of the form, the null hypothesis being mu I minus mu I apostrophe equaling 0, and the alternative hypothesis saying that it doesn't equal 0. When all sample sizes are equal, the family confidence coefficient for the Tukey model is exactly 1 minus alpha, and the family significance level is exactly alpha. When the sample sizes are not equal, the family confidence coefficient is greater than 1 minus alpha, and the family significance level is less than alpha. In other words, the Tukey procedure is conservative when the sample sizes are not equal. The studentized range distribution. The Tukey procedure utilizes the studentized range distribution. Suppose that we have R independent observations where Y1 through YR form a normal distribution with mean mu and variance sigma squared. Let W be the range for the set of observations. Thus, W equals the max of Yi minus the minimum of Yi. Suppose further that we have an estimate S squared of the variance sigma squared, which is based on V degrees of freedom and is independent of the Yi. Then the ratio W over S is called the studentized range, where it is denoted by Q of RV equaling W over S, where the arguments in parentheses remind us that the distribution of Q depends on R and V. The simultaneous estimation. The Tukey multiple comparison confidence limits for all pairwise comparisons D equals mu I minus mu I apostrophe with family confidence coefficient of at least 1 minus alpha are as follows. D hat is plus or minus TS of D hat, where D hat equals Yi dot bar minus Yi apostrophe bar. S squared of D hat is the MSE of 1 over Ni plus 1 over Ni apostrophe, and T equals 1 over radical 2 of Q 1 minus alpha with R and NT minus R. Note that the point estimated D hat and the estimated variance are the same as those in 17.11 and 0.14 for a single pairwise comparison. Thus, the only difference between the Tukey confidence limits for simultaneous comparisons and those in 17.16 for a single comparison is the multiple of the estimated standard deviation. The family confidence coefficient 1 minus alpha pertaining to the multiple pairwise comparisons refers to the proportion of correct families, each consisting of all pairwise comparisons when repeated sets of samples are selected and all pairwise confidence intervals are calculated each time. A family of pairwise comparisons is considered to be correct if every pairwise comparison in the family is correct. Thus, a family confidence coefficient of 1 minus alpha indicates that all pairwise comparisons in the family will be correct in 1 minus alpha 100% of the repetitions. Simultaneous testing. When we wish to conduct a family of tests of the form, the null hypothesis equaling 0 and the alternative hypothesis not equaling 0, for all pairwise comparisons, the family of confidence intervals based on 17.30 may be utilized for this purpose. We simply determine for each interval whether or not 0 is contained by the interval. If 0 is contained, the conclusion of the null hypothesis is reached. Otherwise, we reject it. By following this procedure, the family level of significance will not exceed alpha. Equivalently, the pairwise test can be conducted directly by calculating for each pairwise comparison of the test statistic, where Q star equals radical 2 of D hat over S of D hat, where D hat and S squared of D hat are given in 17.30. The conclusion of the null hypothesis is reached if the absolute value of Q hat is less than or equal to Q of 1 minus alpha R and T minus R. Otherwise, we reject the null hypothesis. A paired comparison plot provides still another means of conducting all pairwise tests. With the Tukey procedure, when all sample sizes are equal, when Ni is N, this plot provides a graphic mean of making all pairwise comparisons. Around each estimated treatment mean of Yi hat dot is plotted an interval whose limits are plus or minus 1/2 of Ts d hat. When the intervals overlap on this plot, the formal test leads to the conclusion that the two treatment means do not differ. When the intervals do not overlap, the formal test leads to the conclusion that the two treatment means differ. In addition, the paired comparison plot shows the direction of the difference. So we know that the When the Tukey procedure is used with unequal sample sizes, it is sometimes called the Tukey-Kramer procedure. When not all pairwise comparisons are of interest, the confidence coefficient for the family of comparisons under consideration will be greater than the specification of 1 minus alpha used in setting up the Tukey intervals. Similarly, the family significance level for simultaneous testing will be less than alpha. The Tukey procedure can be used for data snooping as long as the effects to be studied on the basis of preliminary data analysis are pairwise comparisons. The Tukey procedure can be modified to handle general contrast of factor level means. We do not discuss this modification since the Scheffe method is to be preferred for this situation, which will be discussed next. When the Tukey multiple comparison procedure is used for testing pairwise differences, the tests are sometimes called honestly significant difference tests. The pairwise comparison plot can be used as an approximate plot when the sample sizes are not equal, provided that the sample sizes do not differ greatly. So section 17.6 is the Scheffe multiple comparison procedure. The Scheffe multiple comparison procedure was encountered previously for regression models. It is also applicable for analysis of variance models. It applies for analysis of variance models when the family of interest is a set of all possible contrasts among the factor level means, where L equals the summation of Ci mu I, where the summation of Ci is equal to 0. In other words, the family consists of estimates of all possible contrasts L or of tests concerning all possible contrasts of the form, the null hypothesis where L equals 0, and the alternative hypothesis where L does not equal 0. Thus, infinitely many statements belong to this family. The family confidence level for the Scheffe procedure is exactly 1 minus alpha, and the family significance level is exactly alpha, whether the factor level sample sizes are equal or unequal. Simultaneous estimation. We noted earlier that an unbiased estimator of L is L hat equaling the summation of Ci yi bar dot, for which the estimated variance is equal to MSE of the summation of Ci squared over Ni. The Scheffe confidence intervals for the family of contrasts L are of the form plus or minus S of S L hat, where S squared is equal to R minus 1 of the F statistic of 1 minus alpha R minus 1 NT minus R. Note that the simultaneous confidence limits differ from those for a single confidence limit. Simultaneous testing. Tests involving contrasts of the form L equals 0 and the alternative hypothesis of L does not equal 0 can be carried out by examination of the corresponding Scheffe confidence intervals based on 17.43. The null hypothesis is concluded at the alpha family level of significance if the confidence intervals include 0. Otherwise, we reject the null hypothesis. An equivalent direct testing procedure for the alternatives uses the test statistic F star equaling L hat squared over R minus 1 S squared of L hat. The conclusion is the null hypothesis is reached at the alpha family significance level if F star is less than or equal to F of 1 minus alpha R minus 1 NT minus R. Otherwise, the alternative hypothesis is concluded. The comparison of the Scheffe and Tukey procedures. If only pairwise comparisons are to be made, the Tukey procedure gives narrower confidence limits and is therefore the preferred method. The Scheffe procedure has the property that if the F-test of factor level equality indicates that the factor level means mu I are not equal, the corresponding Scheffe multiple comparison procedure will find at least one contrast out of all possible contrasts that differ significantly from 0. The confidence interval does not cover 0. It may be, though, that the contrast is not one of those that has been estimated. The Bonferroni multiple comparison procedure. The Bonferroni multiple comparison procedure was encountered earlier for regression models. It is also applicable for analysis of variance models when the family of interest is a particular set of pairwise comparisons, contrasts, or linear combinations that is specified by the user in advance of the data analysis. The Bonferroni procedure is applicable whether the factor level sample sizes are equal or unequal, and whether inferences center on pairwise comparisons, contrasts, linear combinations, or a mixture of these. The estimation. We shall denote the number of statements in the family by G and treat them all as linear combinations since pairwise comparisons and contrasts are special cases of linear combinations. The Bonferroni inequality 4.4 then implies that the confidence coefficient is at least 1 minus alpha, that the following confidence limits for the G linear combinations L are all correct, where L hat is plus or minus the BS of L hat. where b equals to the t-statistic of 1 minus alpha over 2g with nt minus r. Testing. When we wish to conduct a series of tests of the form null hypothesis equaling 0 and the alternative hypothesis not equaling 0, we can use either the confidence intervals based on 46 or the test statistic t star equal L hat over S of L hat. If the absolute value of t star is less than or equal to t of 1 minus alpha over 2g with nt minus r, we conclude the null hypothesis. Otherwise, we reject the null hypothesis. It is not necessary that all comparisons be estimated with statement confidence coefficients 1 minus alpha over g for the Bonferroni family confidence coefficient to be 1 minus alpha. Different statements' confidence coefficients may be used, depending upon the importance of each statement, provided that alpha 1 plus alpha 2 through alpha g is equal to alpha. The comparison of Bonferroni procedure with Scheffe and Tukey procedures. If all pairwise comparisons are of interest, the Tukey procedure is superior to the Bonferroni procedure, leading to narrower confidence intervals. If not all pairwise comparisons are to be considered, the Bonferroni procedure may be the better one at times. The Bonferroni procedure will be better than the Scheffe procedure when the number of contrasts of interest is about the same as the number of factor levels or less. Indeed, the number of contrasts of interest must exceed the number of factor levels by a considerable amount before the Scheffe procedure becomes better. All three procedures are of the form estimator plus or minus the multiplier times SE. The only difference among the three procedures is the multiplier. In any given problem, one may compute the Bonferroni multiple as well as the Scheffe multiple, and when appropriate, the Tukey multiple, and select that one is the smallest. This choice is proper since it does not depend on the observed data. The Bonferroni multiple comparison procedure does not lend itself to data snooping, unless one can specify in advance the family of inferences in which one may be interested, and provided this family is not large. On the other hand, the Tukey and Scheffe procedures involve families of inferences that lend themselves naturally to data snooping. Other specialized multiple comparison procedures have been developed. For example, Dunet's procedure performs pairwise comparisons of each treatment against a control treatment only, whereas Hsu's procedure selects the best treatment and identifies those treatments that are worse than the best. The analysis of means. One use of the Bonferroni simultaneous testing procedure is the analysis of means. ANOME is an alternative to the standard F-test for the equality of treatment means. It is conducted by testing the null hypothesis equaling tau 1 equals 0 versus it not equaling 0, and the null hypothesis of tau 2 equaling 0 versus it not equaling 0, and so on for all treatment effects of tau I. The statistics employed are the R estimated treatment effects, defined as tau I hat equals yi dot bar minus mu bar, where I is equal from 1 through R, where mu hat is the least squares mean, given by mu hat dot equals a summation of yi dot bar over R. The estimated variance of tau I is obtained by 17.22, since tau I is a contrast of the estimated treatment means yi dot bar, where the S squared of tau I hat equals MSE over Ni times R minus 1 over R squared, plus the MSE of R squared, with the summation where tau 1 does not equal I over 1 over NN. ANOME is similar to ANOVA for detecting the differences between cell means. However, an important difference between ANOVA and ANOME is that the former tests whether the cell means are different from each other, whereas the latter tests whether the cell means are different from the overall mean. Various enhancements for the analysis of means have been provided, including those in references 17.5 and 17.6. The planning of sample sizes with estimation approach. In section 16.10, we consider the planning of sample sizes using the power approach. We now take up another approach, the estimation approach to planning sample sizes, which may be used either in conjunction with the control of type 1 and type 2 errors or by itself. The essence of the approach is to specify the major comparisons of interest and to determine the expected widths of the confidence intervals for various sample sizes given an advanced planning value for the standard deviation sigma. The approach is iterative, starting with an initial judgment of needed sample sizes. This initial judgment may be based on the needed sample sizes to control the risk of type 1 and type 2 errors when these have been obtained previously. If the anticipated widths of the confidence intervals based on the initial sample sizes are satisfactory, the iteration process is terminated. If one or more widths are too great, larger sample sizes need to be tried next. If the widths are narrower, then they need to be smaller sample sizes should be tried next. This process is continued until those sample sizes are found that yield satisfactory anticipated widths for the important confidence intervals. We proceed to illustrate the estimation approach to planning sample sizes with two examples. The first example are the equal sample sizes. And we have a comparison of the mean tread lives for each pair of brands, mu I minus mu I bar. A comparison of the mean tread lives for the two high-priced brands, where we use mu1 plus mu4 over 2 minus mu2 plus mu3 over 2, and a comparison of the mean tread lives from the national brands and the local brand, where the national brands are 1, 2, and 4, so we have mu1 plus mu2 plus mu4 over 3 minus the local brand of mu3. The other example does the unequal sample sizes, where we have to take a different approach. Now we go on to the analysis of factor effects when factor is quantitative. When the factor under investigation is quantitative, the analysis of factor effects can be carried beyond the point of multiple comparisons to include a study of the nature of the response function. Consider an experimental study undertaken to investigate the effect on sales of the price of a product. 5 different price levels are investigated: 78 cents, 79 cents, 85, 88, and 89. An experimental unit is a store. After a preliminary test of whether mean sales differ from the 5 price levels studied, the analyst might use multiple comparisons to examine whether odd pricing at 79 cents actually leads to higher sales than even pricing at 78 cents, as well as other questions of interest. In addition, the analyst may wish to study whether mean sales are a specified function of price in the range of prices studied in the experiment. Further, once the relation has been established, the analyst may wish to use it for estimating sales volumes at various price levels not studied. The methods of regression analysis discussed earlier are, of course, appropriate for the analysis of the response function. Since the single factor studies discussed in this chapter almost always involve replications at the different factor levels, the lack of fit of a specified response function can be tested. For this purpose, the analysis of variance error sum of squares serves as the pure error sum of squares, the two being identical.